guys
I made that bitch
checking out
famous
Matrices today.
for all the girls that got dick from kind.
And so there are a couple of intentions that you can read, what a matrix and what it can be used for, recognize basic properties, and perform operations on matrices. So the matrix, which we may be aware of, kind of related. I'm going to try and get to how it's related toward the end. A matrix, or a matrice, the plural is matrice, is basically a set of numbers, or a tool that we can use to store numbers in, right? So an example of a matrix might be something that looks like this, and we have 2, 4, -6, pi, 11, and 0, right? And so this is a matrix right here. And so each one of the numbers that goes into this matrix is what we call an element. Alright, so we're going to have a whole lot of definition words today. Matrix, I suppose, is the first one. Matrix, let's leave it in the singular form, is the first one. An element, so an element is something within, so pi is one element of this matrix. The other thing we talk about when we're talking about matrices is its size or order. And so that is the number of rows and the number of columns in that order. So this one here has got 1, 2, 3 rows and 1, 2 columns. So it's a 3 by 2 matrix. This guy here. And often we give it a name. So I'm going to say that this guy is equal to A. So the matrix A is a 3 by 2 with 6 different elements in there. Now, one thing that I always suck at is remembering which ones are the rows and which ones are the columns. So what I always pretend is that I know that if I'm at the movies or if I'm at the footy, I'm in row number something. So if this is our grandstand here of seats, and this is our football ground or a cinema or whatever, then each one of these, this is row 1, this is row 2, this is row 3, this is row 4. And so while we might not use this being one in matrices, we might call this one number 1 up here in matrices. Either way, we know that the things that run like this are what we call rows, because we're seated in row number 3 or seated in row number 2. That's how I remember which ones are rows, and then therefore the other ones have got to be columns. So the other thing we've got to talk about is the position of each of the elements. So as we've said before, when we're talking about the size, this guy here is the row, and then this guy here is the column. And so if we're talking about the position of an element, we can say that the element -6 is in the position A2, 1 is equal to -6, and the reason we do that is because we know that 2 refers to which row it's in, and then 1 refers to which column it's in. So it's that this here is row number 1, row number 2, row number 3, and then we'll make sure they're in yellow, but then column number 1, column number 2. Right, so what we've got is that -6 is in row number 2, column number 1. That's why we say 2, which is the row, and then 1, which is the column. The other thing that we want to look at is just a couple of other types of matrices. So the first one that we can be introduced to is what we call a column matrix. A column matrix, let's call it B, would look something like this. And it would have -2, -1, 17, I don't know, whatever. And so it's in the column. There's just one column within that. And so that is a column matrix, is this guy here. Another one that we can look at is a row matrix, which maybe in your head you're starting to think, alright, -6, come there, put pi in again, 4, and 8, could be more than that, but this is just a single row matrix. The last type of matrix that we want to be introduced to here is a square matrix. Let's say that D is a square matrix. Square matrix is one where the number of rows and the number of columns is equal. So this guy here would be a 2 by 2 square matrix. So he is a square. so then how does this all relate to the matrix itself? It kind of does. The matrices are used for storing large amounts of information, and so one thing that we can use matrices for is when we're generating computer graphics, right? And so this matrix up here, it might tell us about the color intensity at various different positions, right? So one element might describe the color intensity at one point. So the matrix was a computer-generated world, and in that computer-generated world, no doubt, because it was computer-generated, they might have been needing to use matrices in order to generate that world. Although originally my understanding is that the matrices were used to set up systems of linear equations, and we'll perhaps take a look at these in future videos. Alright, so the next thing to do is to take a look at some operations on matrices. The first thing we want to touch base on just quickly is whether a matrix is equal or not. Right, and so a matrix is equal if the size is the same, or two matrices are equal if the size is the same, or the order is the same, and each element is the same. That's finished there. So an example might be that if we know that matrix A, B, C, D is equal to matrix 1, 7, -6, 5, then we can say that A must be equal to 1. We say that A must be equal to 1 because first of all, we know these two are the same size. They are both 2 by 2 square matrices, and each element must be the same. Right? So if they're equal, A must be equal to 1. Alternatively, D must be equal to 5. You get the idea of those other ones there. So that's equivalent. Probably should say equality of matrices. The next thing we can do is look at adding matrices, right? And so we can add matrices if they are the same size. Finish that. So an example might be we had matrix P, and it was 6, -3, 8, and 2. And we had matrix Q. It needs to be the same size for us to add it. Then P plus Q, the matrix P plus Q, is 6 plus 7, which would be element A11, row 1, column 1. 8 plus 3, 8 plus -3, plus -3 is now turned into a negative, and that goes over 2, 2 plus 4. So that matrix P plus Q will be equal to 13, 11, 8 minus 3 is 5, and 6. Whoa, I just realized that was meant to be 2 matrices, TWO. The next thing we're looking at is scalar multiplication of matrices. So a scalar is not a vector. That might mean something for those doing physics. Multiplication. And so a scalar is a single entity number. So like a 4, for example. So a scalar of, a matrix of any size can be multiplied, and if we do so, every element in that matrix get multiplied by that scalar. Let me just pause and write that out. So that's that there, and say if we have matrix G, then 2 times by G, or 2G, is going to be equal to 2 times by 6, 2 times by 3, 2 times by 9, etc. So that's accelerated there. 2 times by 6, which would be 12. 2 times by 3, which would be 6. 2 times by 9, 18. 2 times -7, which would be -14. 8 and then 24. So that would be 2G, where G is multiplied by the scalar 2. The last thing I think that we're going to look at for today is subtraction of matrices. And write it out. So So here we've said that subtraction, like addition, can only occur if they, the two matrices, are the same order. So if we had, for example, a new matrix P, and that was 2, 3, negative 1, 5, and matrix Q, which let's call it 6, negative 2, 3, and 3, then P minus Q, much the same way that addition occurs. In fact, we can rewrite that for the sake of ease. Now we can say P plus negative Q. Right, and so we look at each element in 2 minus 6 is element 1, 1, element 1, 2, element 1, 2 would be 3 minus 3, element 2, 1 would be negative 1 minus negative 2, and then element 2, 2 would be 5 minus 3. So P minus Q, next one down, P minus Q would be negative 4, 0, 1, minus minus becomes a positive, negative 1 plus 2 is 1, 5 minus 3 is 2, so they'll P minus Q. Small note line, there are two other types of matrices we can look at, two special ones. Subtraction wasn't the end, I'm sorry. The first one is called the zero matrix. Zero matrix, and I'm going to put a green underline under that guy. The zero matrix, let's call it a zero matrix or null matrix. We signify him as a capital or uppercase O, and that's equal to 0, 0, 0, 0 in a square 2 by 2 case. Doesn't have to be square. Another, let's call that O1. O2 might be 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. So two different types of null matrices, rather. And the second type of special matrix is the identity matrix. The identity matrix, again, let's whack a green under that. And he is signified by the letter capital I, and he's where the diagonal, both ones. That means that the identity matrix has to be a square. Because to have a diagonal, it necessarily has to be square. To be a square matrix. So another example would be a 3 by 3. Let's call this one I2, this is I1, and it would be 1, 1, 1, and then the rest is filled in with zeros. Okay, we've got ones down. The diagonal identity matrix. Let's take a look at a couple of examples. So given we sort of looked at examples back up there in the blue theory section, basically we'll look at one that's slightly more confusing. So we've got a couple of matrices here, A, B, and C. Now note that they are column matrices. I'll show them down. So the first thing that we want to think is substitute matrices into the equation. So here we've got our equation, which is x times by a plus 2b is equal to c. So what I'm looking at here is that b is multiplied by a scalar 2 and a is multiplied by x. So what we then write is x times by 3 negative 5 plus 2 times by b, which is negative 5, 4, and that is equal to c, which is 2y. So now we need to apply scalar multiplication to this and this, so we think apply scalar multiplication side, so this becomes 3x and it becomes negative 5x, and then that is added to 2 times by negative 5, 2 times by negative 5, which is negative 10, 2 times by 4, which is 8, and that's equal to 2y. There's no scalar multiplication going on this guy. What that allows us to do then is think, alright, well we need to try and isolate x so we can find the value of x. And to do that, first of all, we need to add these matrices. The reason we can add these matrices is because they are the same size. So add matrices on the left-hand side because same size. They are the same size. There's some shortcuts there. So to do that, we're going to multiply, add this guy and this guy. So it'd be 3x minus 10 and negative 5x plus 8 is what the left-hand side of that equation becomes. The right-hand side still stays at 2y. We can't collect like terms between 3x and negative 10, but what we can do now is think about our rules for equality of matrices. So what we're going to do is apply equality of matrices. So with that in mind, what we must recognize is that this guy here has to be equal to this guy here, and then this guy here has to be equal to that guy there. So what we can do then is write a couple of different equations. Equation 1 is going to be 3x minus 10 will be equal to 2, and then equation 2 is going to be negative 5x plus 8 is equal to y. So now we've got to think that we have to solve equations. Now we have to decide how we do this. The first thing I'm thinking is that this guy I can rearrange and solve for x straight away because there's only one variable there. So I'm going to write solve 1, and what I'll do is solve that. I might pause the video and go through it for the sake of time. So solve this guy out of 10 divided by 3, x is equal to 4. So I solved 1 first because it only has one variable, and then use x equals 4 to solve 2. So I'm going to let this here, solve 2. And I'm going to substitute x is equal to 4 first. So we've got negative 5x plus 8 is equal to y, and then we know that x is equal to 4. We want to substitute that in because if we substitute that in, we've only got one variable left over here. So we have negative 5 times by 4 plus 8 is equal to y. And so we can go ahead and then solve that. So negative 5 times 4 is negative 20 plus 8 is equal to y. Negative 20 plus 8 is going to be equal to negative 12 to equal to y. So then we've found the value of y, and the question asks us to find the value of x and find the value of y. There's our x, there's our y, that problem is solved. So the second thing I want to do is just find a blank bit of page and check out a second example using one of those special matrices. Let's bring that up. So here's our second example. Given the matrix A and the matrix B, find the matrix X if A plus X is equal to 0. So I suppose at this point it's timely to point out that often we refer to matrices with capital letters, as you notice in here. So I want to find the value of x, and so when I'm finding the value of anything, often we try and make that the subject. So firstly, we're thinking make x the subject. And we can do this in much the same way we do ordinary linear equations. So we start with a plus x is equal to 0. To do that, we're going to subtract a from both sides. That 0 being a null, not a number 0. So we keep that in mind. So then a is equal to null matrix or 0 matrix minus, sorry, that's going to be x to the front there. That's x. So now we can substitute these guys in, and we know 0, the 0 of null matrix is going to be 0, 0, 0, 0. Now we assume that to be the case because we are assuming we can do this subtraction, and in order to do that subtraction we need to have a 2 by 2 because it needs to be see that 0 minus 3 is going to be equal to -3. 0 minus 5 is -5. 0 minus 4 is going to be -4, and then -7 for the same reason. So then we have gone ahead and we've found the value of the matrix X. So let's put a box around. We're going to finish off with our definition words. There's a couple of them today. Let me bring them up. Now. So, as promised, a whole lot of new jargon to be introduced to, and there are different definitions for you to make sure you copy down with an example. Alright, so matrices are things that hold information, and we can manipulate those in different ways as we've seen today. Good stuff.